Let's take a look at the electrons. Okay, so we've talked about protons and neutrons in the nucleus. Protons' atomic number determines the element. Neutrons are in there. They're neutral. They help stabilize the nucleus. Different numbers of neutrons provide different isotopes for a given element. But electrons are really where all the chemistry happens, because electrons are the particles involved in forming bonds. And that's because the nucleus is the tiny, dense center of the atom. Almost all the mass is in the nucleus. The electrons are way out here, and they can interact with each other. The nucleus is inside that electron shell, so it can't. So the very first thing to know about electrons have a negative charge. Okay? And they have a negative charge exactly equal to the positive charge of a proton, but opposite in magnitude. The next thing to know about electrons is they move in energy levels, or orbitals if you want. Now, depending on how many, so that actually moves in orbitals in energy levels. So what that means is, as you get further and further from the atom, the energy increases, and more electrons can fit. This very first orbital occupies the first energy level, and we can only put 2 electrons on it. If that thing is stable, or if it's full, then the atom is stable and it doesn't want to form any more bonds because all the open spots are full. The next energy level actually has 4 different orbitals in it. And those 4 different orbitals can hold 8 electrons, and if we get to 8, then it's stable. And this pattern sort of continues on and on and on and on, which gets us the octet rule. The octet rule says atoms are stable with 8 electrons. And these are just, I said 8 electrons, 8 valence electrons. Okay? And valence electrons are the electrons in the valence or outer layer. Okay, so those are outer electrons. They're the ones on the highest occupied energy level. If we have 8 there, then it's a good thing for the atom. It's not going to form bonds. It's going to be stable. Now, there's a way to represent this using the periodic table, and let's just take a look at the periodic table. Okay, so the periodic table arranges the atoms based on their atomic number, right? So up here we have atomic number 1, 2. Okay, so that's just showing us how many protons they have. But they're also put into groups, which are these columns, and they're put into rows, which are called periods. Okay? And the reason they're put into groups is because atoms in the same group have very, very similar properties. And the reason for that is they have the same electron configuration on their valence shell. So hydrogen has 1 valence electron. It's a very reactive gas. Okay? Now hydrogen is sort of an outlier. Sometimes you'll see it placed way over here next to helium, and we'll talk about why in just a minute. Okay? So hydrogen, sort of an outlier, but it does fit this column because in this column everything has 1 valence electron. Well, 1 valence electron is really, 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 really close to having a full shell. Because if you consider lithium, lithium has its nucleus in the middle, and then it has that first layer, which has 2 electrons on it, which would be stable if it was done there, but instead it's got a 3rd electron, right? Because that 3rd electron has to balance a proton, and so that 3rd electron's out here. Well, this has got 7 empty spots, which makes this incredibly unstable. It doesn't have 8, it has 1. So lithium will actually give away an electron to go back to looking like helium, which is stable with 2. Okay, so lithium actually only wants to have 2 valence electrons, so it'll get rid of this 1 outer one and become stable. Beryllium does a similar process. Okay? So everything in column 1 has 1 valence electron. Everything in column 2 has 2 valence electrons. Then we get to this B group in the middle. Okay, these are called the transition metals, and we will talk about these, but for now we're going to ignore them. Okay, the transition metals for now are a little bit more complicated than we want to get into. Okay, so we go 1A, 2A, and then we skip all 10 of these columns in the middle, and we're going to start this over. And instead of calling this 13, we're going to call this 3A. And instead of 14, we have 4A, 5A, 6A, 7A, 8A. And when you look at just the A group number, that tells you the number of valence electrons. So hydrogen has 1, helium has, helium's that other outlier. It only has 2 because it's only got 2 protons. But again, there's only 2 elements in the first row because that first row, that first energy level, only holds those 2 electrons. Then we go to the next period. Lithium has 1 valence electron, beryllium has 2, boron has 3, carbon 4, nitrogen 5, oxygen 6 valence electrons, fluorine 7 valence electrons, and neon 8 valence electrons. Okay? Now, This row, or sorry, this column over here, this family is called the noble gases. They don't do anything at all. They are stable. They already have their outer energy level full. They don't need to gain electrons. They don't need to lose electrons. They're not going to form bonds. This column right here, called the halogens, is very, very similar to this column over here. These are the alkali metals, by the way. The reason they're similar, even though they're gases instead of metals, or non-metals instead of metals, is because they have the exact opposite problem that the alkali metals have. If you consider fluorine, fluorine has 9 protons, so 9 total electrons. Well, that first energy level holds 2, and then the next 7 electrons fill in on this next energy level, 5, 6, 7. That leaves only one open spot, and if it could fill that open spot, then this element would have 8 valence electrons, and it would be an incredibly stable, happy element. And so for these elements, because they all need to gain one more electron in order to become stable, they're very, very reactive as well. So if you're thinking this column over here, these metals, could probably give their electrons away to these halogens, these nonmetals, and then everybody would be happy. And that happens. That's what an ionic bond is. And we'll talk about that in the next little video. The last thing I want to show you are these electron dot diagrams. Okay. Now these are just an easy way to keep track of what's going on with elements. Okay? And what you do is you just draw the symbol surrounded by dots, okay? And each dot is a valence electron. Now there are a couple rules when we draw electron dot diagrams. No side gets 2 until all sides have 1. Okay? And you can never have more than 8. No sides get 2 until all sides have 1. No more than 8. Hydrogen breaks this rule. Hydrogen only needs 2. Okay. Helium also breaks the rule. Only 2. So if we take a look at drawing an electron dot diagram, I know carbon is element number 6, but I also know that it's in the 4th column on the periodic table, or 4A. So carbon, if I draw its electron dot diagram, I'm going to go 1, 2, 3, 4. It doesn't matter which side I start on. Fluorine, we already talked about, was in group 7, so it's got 1, 2, 3, 4, 5, 6, 7. Now the reason we only draw 1 per side and then we start pairing them up afterwards, paired electrons are happy. They don't want to form any bonds. Unpaired electrons, well, he's got an open spot next to him. Okay, so unpaired electrons will form bonds. So electron dot diagrams are just an easy way to keep track of valence electrons to try to predict what kind of bonds atoms can form, or how many bonds atoms can form.